Majesty's World Science Channel. Today, in this video, I'll be handling a guide to a titration and also salt analysis. The titration is a titration between, according to specification, 8.4 grams sodium hydrogen trioxocarbonate 4 versus a solution of HCl. The standard or the specifications is that you should dissolve 8.4 grams of sodium hydrogen trioxocarbonate 4 per dm cube of solution So we'll find the molarity, while that of acid is that you are instructed to dissolve about 8.6 cm cube of 36% concentrated HCl in every 1 dm cube of solution. So we will also find the molarities. So when we find the molarities, in finding the molarity, we can now find the accurate endpoint theoretically. So to find the molarity of the base, which is actually an acid salt, though, but is acting as a base here. Now, how do we do that? First of all, we have to find the molar mass of sodium hydrogen trioxocarbonate 4, which is automatically 84 because sodium is 23, hydrogen is 1, that's plus 1, carbon is 12, plus oxygen is 16, and 16 times 3 is 48. And when you sum up all this, you get 84 grams per mole. So the molar mass is 84 grams per mole. Then to get the molar concentration, that's the molarity is always gotten by dividing mass concentration all over molar mass. Mass concentration all over molar mass. So, and the mass concentration is already given as 8.4. Then the molar mass has been gotten as 84, so that makes our work easier. Therefore, 8.4 divided by 84 automatically will give you 0.1. This is a cheat you will know in every calculation in science. When similar numbers divide themselves, differing by the position of the point, in this form, it will always give you 0.1. What I mean is that even when we have 9.4 divided by 94, it will still give us 0.1. Even if we have a 1.0 divided by 10, you see the difference is in the point position in the middle, but the number is the same. It will give us 0.1. But when the numbers are not the same, it will not be the correct answer. Let's assume this is 14 divided by something like 15. We are no longer that's 1.4, sorry, divided by 15. We will not get the same thing because 14 and 15 is not exactly the same digit. That's just by way to save time in exam. When you have the same digit but different the position by just one places, but the reverse should be 10. For example, we have gotten 8.4 over 84 as 0.1. The reverse is now 84 over 8.4. That should also be 10 in this case, always, thus to save time in most calculations. Okay, so this is now established that we will now write 8.4 all over 84, which will give us 0.1. So molarity of B, which is a solution of sodium hydrogen trioxocarbonate 4, is automatically 0.1 mole per dm cube. We can use capital M, or you can write it mole per dm cube. So now let us see the molarity of the acid. Molarity of the acid in question, which is actually HCl, this might take a longer time or further training. If you want to be trained as a chemistry teacher, you can experimentally get even the SG. From the SG, you can determine the molarity actually, or you can use standardizing. What I mean is that you can titrate the volume you are asked to measure with sodium trioxocarbonate 4, which is always a primary standard, a already known strength, and you can determine the molarity. But there are theoretical ways for you to know it that might require further training with me if you're interested. But since they told us that it is HCl and the percentage is 36, automatically 8.6 cm cube of it in every that's per dm cube of solution automatically means 0.1 also. So the molarity of HCl is equal to 0.1 mole per dm cube. So we have gotten the molarity of the two the acids and the bases, which makes it easier now for us to calculate our endpoint. To calculate the endpoint, what do we use? We use our normal titration equation. Now we have CAVA all over CB VB equals NA over NB, where Na is the mole ratio of acid and Nb is the mole ratio of base in a balanced chemical equation. For us to get that, we have to balance the equation between the acid and the base in question. So HCl neutralizing the acid salt sodium hydrogen trioxocarbonate 4 to obtain a normal salt, which is sodium chloride plus water, of course, then plus CO2. So checking the equation is balanced just naturally, so that the mole ratio of acid to base is 1:1. So our Na is 1, our Nb is also 1. Therefore, we go back to our formula over here and substitute our values. It's only Va that is unknown. That is our endpoint. So what do we do here? We have that Ca will now be 0.1 from our previous calculations, as you can see here already. Then our Va is unknown. That's what we are looking for. The Va is unknown. Maybe we'll write it in blue to show the one we are looking for. Okay. Then all over CB is still 0.1 times, you can use, this 25 is actually volume of pipette, as we all know. So there are two standard volumes we use here in Africa, 25 or 20 cm. So if you use 25, you put 25. If you use 20, you put 20 here. Now, but remember that one school should use one particular volume. So it's now equal to what? Na is 1, Nb is 1. Since this is 1/1, what can we do to make this thing 1/1? It means that Va is automatically 25. It's a simple reasoning, because the mole ratio is 1/1. It means that the denominator and the numerator have to be equal, because it's only when equal numbers divide themselves before you get 1, and that is 1/1. But all the same, if you don't get the logic, we can still do the normal mass, cross multiply. Therefore, 1 times, we will now have that 1 times 0.1 times Va is equal to 1 times 0.1 times 25, such that Va is dividing both sides by 0.1, of course. And then if you divide here by 0.1, because 1 times 0.1, you find out that Va remains, this remains. So the answer is 25.0 cm cube. This is the theoretically accurate endpoint, but for exam purposes, it doesn't really mean. If you really want to do the practical and they are doing the real titration, you watch my videos here on titration. I have not less than 15 practical videos on titrations, so that's why I decided to guide this one theoretical, so you can watch even the double indicator titration, where you are required to use more than one indicator in a titration. So can watch those videos. But now, if you are doing practical, it is not assured that you must get this 25.0 on the dot. Practically, because of other variables, you might get 24.60. It is still not too bad. Somebody can also get 26.10 is not also bad. So within this range can be accepted, but just know that what the examiner marks is how your student's titer value rhymes with the teacher's report, with the value the teacher filled in the teacher's report form. So that means you advise your students not to vary with more than 0.2.
Wait a minute. Have you heard about Majestic Table? It was designed and recommended by Sir Majesty himself. Here it is. The amazing thing about the Majestic Periodic Table is that it provides a clear and colorful classification of elements from P block metals to metalloids to liquid metals. It also shows the boiling and melting points of all the elements. It also has the unique feeling of electrons in the shells of each element.
Enhance the easy learning and teaching of chemistry in schools, in universities, secondary schools, in research institutes. So this Majestic Periodic Table, demand and special demand, as you can see that space there highlighted, that is where you can include the name of your school, or if you are dedicating it to anybody, you can write there, because you can print it to any size you like. In a majestic size, the resolution will never be affected. So it took me about 3 months to design and provide these informations, but thank God the table is here. What made me to design this is that I discovered that these tables I see in the internet, the one I see in the market, they are not as informative as I want. And then some of them are not updated. Some still retain the fact that we have, there are like, some still see promentum as not being radioactive. Some might see them as artificial element, but it is still is a naturally occurring element, of course. So there are some modifications that this table has been made to include, and that makes it majestic.
This is super majestic.
Much love.
When I say more than 0.2, it is plus or minus 0.2 cm. Sometimes students will confuse 0.2 to mean 2. No. Meaning if your teacher has filled 24 sorry 0.60 and you as a student is getting something like 25.60, you are wrong. You are very far. You are more than 0.2. Though the correct endpoint is supposed to be 25 and your teacher filled 25.60 and your own is 25.0, you are 0.2 above, which makes you lose mark in that average titer. So you are advised to be within the endpoint range, and this requires that if you have not trained your student well and there is no accurate apparatus, you will tell your students maybe indirectly the range of your end point. But students that are trained well will not vary with more than 0.2. My students don't vary, since your preparations are correct and accurate and your apparatus, your burette and pipette are all perfect. So this is it for the end point. Then for the likely question, in this type of titration, you might be provided with phenolphthalein and methyl orange. So between these two, phenolphthalein and then the methyl orange. So between these two indicators, which one is suitable? Remember, the titration is between an acid salt, which is a carbonate actually, and an acid. Do we use methyl orange here or do we use phenolphthalein? The most suitable indicator between these two is methyl orange. That's the indicator to be used. So what is the reason? Because when you look at if I'm the examiner, I will provide these two in the teacher's instruction to confuse, but phenolphthalein will not be used in this type of titration. Reason, you can watch my video in the double indicator titration where the titration was between HCl and sodium carbonate. Remember, if the titration is between HCl and sodium carbonate, where they mixed the sodium carbonate and sodium hydrogen carbonate. Yes. So I think Ghana wrote such exam, HCl versus mixture of sodium carbonate and sodium hydrogen carbonate. The phenolphthalein can only react when it's sodium carbonate, but sodium hydrogen carbonate, phenolphthalein is colorless in sodium hydrogen carbonate, because it's an acid salt. So there is, and remember, phenolphthalein will also be colorless in HCl, so it is not going to serve as a suitable indicator. So the suitable indicator is methyl orange, because that is the correct, due to the pH transition range of methyl orange, it makes it suitable for such titration. So other questions might follow. Remember, you might be asked precautions, then know how to calculate the volume of CO2 evolved at STP, know how to relate the mass of salt formed with the acid salt or equally with the HCl. All these things, there are many possible questions that can come. Then you do yourself a favor to watch many of my tutorials here on titrations and possible questions, or you can equally come for private coaching if you need more, or watch most of the free videos. Now we move on to the salt analysis, the analysis of I'll be handling the analysis of zinc trioxocarbonate 4. You'll be listening to what I'm saying. First of all, this carbonate is an insoluble salt. It's insoluble first, and this is also commonly in nature, it occurs as a calamine lotion, the one we use in treatment of chicken pox. So, but here I'll be explaining the analysis. First of all, action of heat on this, on zinc trioxocarbonate 4. What will happen if you heat zinc trioxocarbonate 4? There will be tendency of decomposition, which the equation, you might not be required to write the equation, but I'm writing it so that you understand what you report in your salt analysis. To give you zinc oxide plus CO2. So in your report, you just, in observation, you say a yellow residue formed, or sample C turned from white to yellow. So action of heat on zinc carbonate changes it from white to yellow, because zinc oxide is yellow when hot, but when cold is white. Zinc carbonate itself supposed to be white if that is stable. So what gives this zinc carbonate a yellow color when hot is the zinc oxide, not that the zinc carbonate is yellow when hot and white when cold. Rather, it is the zinc oxide that is yellow when hot and then white when cold. Then don't confuse it with lead oxide. Lead oxide is yellow when cold and then red and some other colors or yellow also when hot still. So lead 2 oxide is never white, but zinc 2 oxide is a white when cold. White when cold, but white when cold. That's at room temperature, but yellow when hot. This is attribute to zinc oxide. So then you will also need to report that colorless, odorless gas evolved during the action of heat. Yes, there will be evolution of gas when you heat zinc carbonate. So you should also get ready to distinguish between zinc oxide and the zinc carbonate, and that is what I'm explaining here. I'll still give you a table of test, observation, and inference here in this video that will help you report well, but this is the real teaching and the explanation. So you also get ready for this, and that's what I'm doing here, to differentiate between zinc oxide and zinc carbonate. Zinc oxide is yellow when hot and when cold. On heating zinc oxide, there is no evolution of gas, but when you heat zinc carbonate, it will still turn from white to yellow, but the difference is that there will be evolution of gas, carbon 4 oxide. So that's the first difference. Another one is that if you add HCl or any other acid, action of HCl or any other acid, another difference is actually the action of acid on any of on both, meaning on zinc oxide. If you add an acid to zinc oxide, there will be no effervescence, there is no evolution of gas, but it will dissolve in acid, because zinc oxide is amphoteric. It behaves as a base in the presence of acid. It will also dissolve in base. Then zinc oxide, action of acid on zinc oxide, there is no effervescence, but they will dissolve. But action of acid on zinc carbonate will yield or lead to what we call effervescence. That is, effervescence, the evolution of gas from a liquid. Gas will come out. Yes, like you open a fizzy drink and that gas is actually CO2. So these are the ways one can at least distinguish from sodium carbonate, from zinc carbonate and then zinc oxide. The next thing is that there will be tendency of you being required to dissolve or add that zinc carbonate, add few drops of HCl. Then you might be told to heat and allow to cool, filter possibly. Yeah, you will be told to filter possibly because the whole carbonate must not dissolve. So when you filter the undissolved carbonate, and now you'll be told to analyze the filtrate. So you now be told to the filtrate, maybe to the first portion of the filtrate, add sodium hydroxide. Okay, let me use a normal pen, but I'll still make a table. Add sodium hydroxide in drops and in excess. This time around, they are testing for zinc-2 ion because zinc in zinc carbonate is not in form of zinc-2 ion. But when you now add acid, it will dissolve in that acid. If it is HCl, it will form zinc chloride. If it is HCl, it will form zinc sulfate, which is now soluble to give you this zinc-2 ion. So you now just go and study the test for zinc-2 ion. But you cannot confirm that zinc-2 ion when the zinc is still attached to the carbonate in form of zinc trioxocarbonate 4. No, it will not be easy to detect in that form. So you must convert it in a form where there will be zinc ion in a soluble form, converting the zinc carbonate from the insoluble form to a soluble salt, which is either the chloride or the sulfate or the nitrate. So HNO3 can also be used. Zinc nitrate is also soluble. Now, sodium hydroxide in drops and in excess to the sample will give you an observation, which will be white gelatinous precipitate formed in drops, which dissolves in excess. Your inference should be aluminium or zinc-2 ion present, since they said gelatinous. Don't say lead because lead is not gelatinous. Then to the second portion of the same filtrate, you will be required to also do the same, but this time around with aqueous ammonia. Your observation will still be the same as you observed with sodium hydroxide, but your inference will not be the same. Observation here will still be white gelatinous precipitate, which formed in drops and then dissolves in excess or soluble in excess of aqueous ammonia. Inference will be zinc-2 ion confirmed. So let's go straight and make the table for the salt analysis from what I've been saying. Remember, you are on with Sir Majesty Easy World. You endeavor to subscribe and share this video. Much love from me to you. I cannot do without you, and you expanding this science community should be the payback and should be another way to support us. If you are not the candle producing the light, endeavor to be the mirror reflecting it. Okay, so we are going to make a table here. Okay, I want to use let me use shapes and make line. Okay. Okay, so as usual, we have our observation, test, and inference. So I'm shifting to give more space. Then we have this. We now go back to writing with our pen. This should be test. This should be observation, and then inference. Okay, you might have a serial number to number the practical. Where the test is sample C plus heat. plus cool is possible. Observation: white, I say yellow when hot and white when cold. Yellow when hot and white on cooling. Then there will be effervescent. You can also say effervescent occurred. Effervescence occurred. Colorless, odorless, odorless gas evolved. Gas turned lime water milky, of course. That's possible. Or you say which turned, there will be no full stop. You now say which turned lime water milky. So your inference is just zinc oxide, probably. Say zinc oxide present, CO2 gas from probably CO3, that's trioxocarbonate 4 ion, or hydrogen trioxocarbonate 4 ion. Okay, then the next possible thing from my previous explanation is to dissolve some part of C in an acid, C plus dilute HCl C plus dilute HCl. They can use H2SO for any other acid because the resulting zinc salt is soluble. So now what will happen, you just say effervescence occurred, colorless, odorless gas evolved, just like we reported exactly up there. Colorless, odorless gas evolved, which turned lime water milky. Lime water milky. So it depends on when they are telling you to heat. Now, if they tell you to heat and possibly filter, if this one is now say plus heat plus filter, let's assume this was added, then you'll be forced to say C dissolved in acid, or part of C dissolves in acid. There will be no observation on heating. Heating is just to facilitate the solution. You just tell them that C dissolves in HCl. If they say H2SO4, you say H2SO4, and your inference here should still be CO2 gas from HCO3 minus or CO2 or CO3 2 minus. Over here should be no 2 minus, please. This should be hydrogen trioxocarbonate 4 ion, which is HCO3 minus, not 2 minus. Okay. Then, due to the fact that they tell you to, you just say that C is soluble in acid. Yeah, you have done the justice. Then, when you are required to divide into portions, so what you will now do is first portion of the filtrate, first portion of solution from or filtrate. If you are not asked to filter, don't say filtrate. First portion of solution from whatever numbering. It might be 3CI or CII above or BII above, depending on how it was numbered, plus NaOH in drops plus excess. Put the state of matter, aqueous, that's to show a solution. What should be your observation? White gelatinous precipitate. White gelatinous precipitate. White gelatinous precipitate. You can use PPT, precipitate, formed in drops, which is soluble in excess, to form a clear solution. If you like, excess of NaOH is important, you mention it. So you just say aluminium or zinc 2 ion likely or present. Then now say second portion, the same grammar but this time around, plus aqueous ammonia in drops plus excess. Now still report exactly what is in this column. Bring what is here down here again, but the difference is that your observation will now be, your inference will now be just zinc 2 ion confirmed. The reason is because it's only zinc ion that will form white gelatinous precipitate that will dissolve in excess of aqueous ammonia, even though the observation remains the same as here, but because of different reagents, here is sodium hydroxide but here is aqueous ammonia, that's why we say zinc confirmed. Okay, so this is it for the practical guide on titration and this salt analysis. Also learn how to distinguish between the sodium trioxocarbonate 4 and then sodium hydrogen trioxocarbonate 4. I have a video on that on this channel. I've told you how to distinguish one. There will be action of it. Phenolphthalein is what I mentioned here, so just go for the detailed video. Thanks for watching. Subscribe. Bye for now. I love you.